Hello everyone. In this lecture, we are going to discuss probabilities of density and probabilities of false alarm. So, in previous classes, we discussed about false alarm. The false alarm, uh, so it is the term which is used in detection of the signal in the presence of noise. So, the detection of the signal in the presence of noise was based upon uh, threshold detection technique. So in threshold detection technique, so we made certain threshold levels. So if the echo signal from the target crosses the threshold level, then we are going to represent, or we are going to consider that as a that echo is from the particular target only. So if we made that threshold very low, so if we take that threshold level at a very low level, so at that time the noise also crosses the threshold level. The noise from the clutter also causes the what uh, we are going to consider that as also a target. That is called as what? The false alarm. The false alarm is nothing but if the noise crossing the threshold level, that is called as false alarm. So in this class, we are going to consider probabilities of such false alarms. So by using envelope detection or envelope detector technique. So this is the super heterodyne receiver, okay, and it consists of IF amplifier of the bandwidth BIF and a second detector and video amplifier. And video amplifier which is having the bandwidth BFE, okay, and threshold where the in the threshold the detection decision is made. Here the IF amplifier, second detector and video amplifiers, these are called as envelope detector. So these three blocks are called as envelope detector. So here the video amplifier output, here the video amplifier output is the envelope or the modulation. It is the modulation of the IF signal. So here we have applied the IF signal and we have modified it in this video amplifier. So for that we have certain conditions. The first condition is that the envelope detector requires that the video bandwidth, so this the bandwidth in the video amplifier BV, it is BV in this in this video amplifier the bandwidth will be BV, that should be greater than or equal to half of this bandwidth, half of the bandwidth of the IF signal or IF bandwidth, okay. And one more condition, that is here the center frequency FIF, the frequency of this block should be very much greater than this. The frequency the bandwidth should be greater than or equal to half of this bandwidth, whereas the frequency of this IF amplifier should be very much greater than this video amplifier, okay. So the envelope detector, what it does, this envelope detector, these three blocks are called as envelope detectors. So this envelope detector passes the modulation and rejects the carrier signal. So here we are going to consider probability of the false alarm. So the that is the receiver noise, at the input of the IF amplifier. Here we are going to represent the receiver noise at this input of the IF amplifier by using Gaussian probability density function with a mean value equal to 0. So that is represented as P of V which is equal to 1 divided by square root of 2 pi sin naught into exponential of minus v square divided by 2 sin naught. This is the equation number 1, where p of v into dv, it is the what? It is the probability of the finding the noise voltage phi between the value of phi and v plus dv. So these are the what? Threshold levels, threshold voltage levels. So what we are going to do? We are going to finding the noise voltage phi between these ranges. Okay, and that is represented as p of phi into dv. So here we are going to consider the noise here, only noise when the noise is present. So that we are going to consider by using the Gaussian probability density function. And here one more term we have, that is a sin naught. Sin naught is the what? It is the mean square value of the noise voltage. Okay, it is the what? The sin naught is the mean square value of the noise voltage. So if it passes this with the IF amplifier, if it passes this signal with IF amplifier, then the PDF of the envelope, so here the output is going to generated, that is envelope R is given by. So we have fed this signal into this IF amplifier and we are getting the output at this that is envelope detector. So here the output can be represented as P of R. The P of P become P of R here, that is equal to R divided by sin naught into exponential of minus R square divided by 2 sin naught. This is the equation number 2. So in continuation with this, so the what we have done, we have passed this, the input noise into the IF amplifier, and we have taken the output from the video amplifier. The probability that of envelope of the noise voltage will exceed the voltage threshold or threshold voltage Vt is the integration of the PR of evaluated from the, so that this is the range here, Vt, that is the threshold voltage level, to the infinite. So now it will become, so here we have R term, it is varying in between Vt to infinite. So for that, if we have the integration Vt to infinite R divided by sin naught into exponential of minus R square divided by 2 sin naught into dr. So if we integrate this, we will get this term, that is exponential of minus Vt square divided by 2R we will get. That is what the probability of R in between the voltage levels Vt to infinite. Okay, so this is the what noise which is contaminated in the radar receiver. So here we have an graph. So this is the noise represented. So noise, what it is doing, it is crossing here a threshold level, it is the threshold level. Okay, so it is the what, along this axis we have envelope of the noise voltage, and along this axis we have x-axis we have time. So this is the what noise, it is represented, noise alone is present. So here we don't have any noise, we don't have any target echoes here, we just have a pure noise here, and the noise, it is crossing the threshold level. So here it is also crossing, here it is crossing, and here it is crossing. So when it crosses the threshold level, when the noise crosses threshold, when we make threshold at a very low level, at that time the noise also crosses the threshold level. So here the average time between the crossing of the decision threshold, but the noise alone is present. the average time between the crossing of the decision threshold when the noise alone is present, and this term is called as a false alarm time. Okay, the false alarm time, which is nothing but what the average time between the, here we have, this is the what, this duration is nothing but a tk, such what times, the average times between the crossing of the decision threshold when the noise alone is present, that is called as false alarm time, and that is denoted by TFA. And TFA, which is equal to limit n tends to infinity 1 divided by n into summation k equal to 1 to n into tk. So here tk, it is the what, it is this time between the crossing of the threshold voltage. So it is nothing but what, from this to this, it is what tk. Tk is the time between the crossing of the threshold vt by the what, noise envelope. So here the false alarm, so this is the what, the false alarm, the probability of the false alarm can be represented in terms of the false alarm time. Okay, that is nothing but a false alarm probability. So here we have false alarm probability, so that is given by PFA. This is the what, false alarm probability, and it is the ratio of the time the envelope is actually above the, here the envelope is actually above the threshold to the total time it could be above the threshold. So that is nothing but a PFA. So that is given by summation k equal to 1 to n tk. So this amount of time, this is the, this amount of time is as a small tk, it is tk plus 1, it is tk plus 2. So here we are going to take such averages, tk average, which is equal to 1 divided by tfa into b. Okay, so this is about the what, a pulse alarm time. So in continuation with this, we'll discuss probability of detection. So in we have discussed till now, we have discussed probability of noise. So now we will discuss probability of detection of the signal. So here we are going to consider a echo signal that is represented as a sine wave of amplitude A, and along with this signal, along with the echo signal, a Gaussian noise at the input of the detector we are going to consider. So, and that is represented by the envelope of R at the video amplifier is given by PS of R, which is equal to R divided by sin naught into exponential of minus R square plus A square divided by 2 sin naught into I naught of RA divided by sin naught. This is the expression or equation number 1. So where the I naught Z, so this thing I am going to consider as a Z, that is I naught Z is the Bessel function, it is modified Bessel function, okay, of 0 order, it is the 0 order modified Bessel function, and argument Z, also which is having the argument Z. For a large Z, this expansion will become I naught Z, which is equal to e raised to Z divided by square root of 2 pi Z of 1 plus 1 divided by 8Z plus so on. This is the expression number 2. When the signal is absent, that is a equal to 0, so at that time this expression reduces to uh, noise. Okay, noise alone equation. So we have discussed that was previous. So here the probability of detecting the signal is the probability of that the envelope R will exceeds the threshold voltage. So here the echo signal exceeds the threshold level, then we are going to consider that is the what the target is present. So that is given by Vd, which is equal to integration over Vt to infinite Ps of R into dr. So this is the what, when this we are going to consider this equation when the echo signal crosses the threshold level. And here we have two equations, the first equation and second equation. So this is the what, the equation, the echo signal with the noise, but whereas here it is the what, it is the envelope R. Okay, the probability that the envelope R. So the equation number 1 and 2 are the function of the signal amplitude A, threshold voltage Vt, and the mean noise power psi naught. So we are going to consider these with a function of the signal to noise ratio, and then we can represent the signal to noise ratio. Signal as well as noise can be represented as A divided by psi naught raised to 1 by 2, which is equal to signal amplitude divided by RMS noise voltage, and this is also equal to square root of 2 into 2, that is RMS signal voltage. So this is also represented as like this also, it is 2 into signal power divided by noise power whole raised to 1 divided by 2. So we can take one more form of this, that is 2s, that is s is signal, 2s divided by n whole raised to 1 divided by 2. So this is the what, the signal to noise power ratio. Okay, so this is nothing but a signal to noise power s divided by n, or it is s divided by n, or a divided by psi naught raised to 1 by 2. Thank you.